Okay, now that we've learned how to create ionic compounds and predict what their compound should be, we're now going to go through the rules for naming compounds. And there are three different ways in which you can name compounds and three sets of rules. The first is molecular or covalent compounds. The second is ionic compounds. And the third are acids, which have their own naming scheme. And so for molecular compounds, what you're looking for is the fact that molecular compounds will have only nonmetals. And so when you look at a compound, what you have to first identify is it molecular or covalent? Is it ionic? Or is it a acid? Depending upon what you've identified, then you go through a set of rules to name the compound. And so for molecular compounds, this is probably the easiest one. What you're going to do is you're going to name the compound itself, or name each element in the compound, and you're going to identify how many of the elements are in that compound using Greek prefixes. I'll show you that at the on the next slide. And so Greek prefixes are like this. If there are one, you use the term mono. If there are two, you use the term di, and you put that in front of the element's name. 3, tri. 4, tetra. 5, penta. 6, hexa. 7, hepta. 8, octa. 9, nona. And 10, deca. And we're going to put this prefix in front of the element's name to indicate how many are there. Now, there is a rule. The first atom in the compound, if there's only one of them, do not use mono. Okay? In terms of writing them out, the prefix ending, if it ends in A or O, or the element begins with a vowel, drop the A or O when you're doing converting the name. The name of the first one is usually the one that is most metallic or least electronegative, and the last symbol. What you do is you use its name, but you drop the ending and you add "ide." So all compounds that are molecular covalent will have an element's name, and it will end in the element's name that's converted into "ide." Now, the Greek prefixes are the subscripts on the compounds. And again, you'll need to know the prefixes here, and these are the Greek prefixes. So let's try a few. And so the first would be carbon dioxide. Using my rules, the first element is carbon, so that's easy enough to write, carbon. The second is, you see the prefix di and oxide. Oxide comes from oxygen, and so oxygen is converted into oxide, so I know I have oxygen. The di means I have two, so there's carbon dioxide. Here, the first element is phosphorus, and here the second element is chlorine, but when we name it, we change it to chloride, but there's a 3 here, so I have to use a prefix, trichloride. So I've taken chlorine and changed it into chloride, and I've made sure I told myself that I have 3 of them. I do not use a mono because there is only one, a phosphorus, and by writing the P, I've indicated that I have one. And so the next compound would have 2 phosphorus atoms and 5 oxygen atoms. And so if I do that and I write what the compound would be, P2O5. So this would be diphosphorus, and 5 would be pentachloride. And so here are 3 examples. Now, if you are in a section that you're only doing covalent or molecular compounds, it's easy to run into and run these things. You only use tri, tetra, mono when you are working with compounds that are covalent. Here, what I'm going to ask you to do is look at a document in which, or a workflow. What we're going to do is we're going to look at the first element, and if the first element is molecular compounds, all nonmetals, so this is the first element, I'm going to add a prefix to the element's name, but I won't use mono. Here are all of the prefixes that I can use. The second element, you add a prefix to tell me how many I have, and then you change the element's name by ending "ide" to it. So that's how we would approach a molecular compound. The rules for ionic compounds. So this is ionic compounds. What you would do is you would look at the compound, and an ionic compound is either going to begin with a metal, which is most often, or you're going to get one of the ions, the polyatomic ions, that are positively charged, and that most often is ammonium. And so the rules for this, the cation itself is the same as the name of its metal. And so if I see the first element is sodium, then the name of that is sodium. If the metal is lithium, it is named lithium. And for many metals, that is all we need. But if the cation is in transition metals, and remember, transition metals have an issue because they have multiple charge. That means they can be more than one charge, so I have to tell you what charge that is. And so there are a couple other exceptions like tin and lead, not exactly in the transition metals, but large enough, and we can see that they have multiple charges. What we have to do is write a Roman numeral in parentheses to indicate what charge that is. The exceptions to this is zinc and silver, because they will only form those charges. I do not have to tell you. Zinc is a +2. It will always form a +2, will not form anything else, so I don't use the Roman numeral. Silver the other way forms a +1, nothing else. And so you can see copper here with a 1+. I use the Roman numeral to indicate that it is a copper +1. Copper exists as a +2 state, and so I can write copper in a +2 state. Now, there is a much older naming system in which us and ic are used, and so Q+ is the smaller of the charge, Q' is the larger of the charge. You don't see that too often anymore, but you may walk into a laboratory and you'll see those names on an old bottle of chemicals, so you'll need to know that. Cations formed from nonmetals end in like the ammonium and the hydronium ion. The ammonium is on your list, you need to know it. The hydronium is something that we're going to look at, and this is what happens when acids are added to water, and so we'll look at the hydronium later. Once you've named the cation, then you have to work and start naming the anion of an ionic bond. Now, anions are a little bit more complicated because there are multiple kinds of anions. And as you go through and do the TRQs on the ions and cations and anions, what you're going to find is ions that are made of one atom, one kind of atom. They have their ending changed to "ide," very similar to the naming mechanism that we used for the molecular compounds. So sulfur becomes sulfide, chlorine becomes chloride, bromine becomes bromide, oxygen becomes oxide, phosphorus becomes phosphide. Okay, and so there are anything that has just a single element, it becomes an anion. I'm going to change it to "ide." There are some exceptions. There are some group names or polyatomic ions that have "ide" in them. So hydroxide, cyanide, and peroxide are ones you need to know. But The ones that have their own unique name, you need to know those, and that's a memorization thing. Polyatomic ions containing oxygen, okay, with more than two members have an order in which they are named. And so you can do one of two things. You can learn this naming scheme, or you can learn each and every single polyatomic ion by itself. I don't care what way you want to go about learning that, but here is the reason why we name these compounds the way that we do. Now, here it is. Oh, sorry, take that back. Here it is. Eights. The ion that has an element in oxygen that makes an ion, the one that is most often found in nature is the 8. Now, there's no rhyme or reason to how many oxygens are added or what charge it is. You can have, we're going to see 8s have multiple different numbers of oxygens and multiple different numbers of charges, but the one that is found most often in nature is called the 8. If you go one below, it's called ite, and if you go one below that in terms of numbers of oxygens, you get the hypoite. If by chance you find one that is one more oxygen than the normal, it is going to be the per 8. So what does this mean? All right, so here it is chlorine bound to oxygen. So chlorine bound to oxygen is 3 as a 1 minus charge. This is called the chlorate ion. Now, here is that's an ion that is very similar, just one less. This is the chlorite ion. Here is one that is 2 oxygens less. It's the hypochlorite ion. Here's one that has 1 oxygen more than the normal, and that's the perchlorate ion. Bromate, minus 1 charge. Bromite, minus 1 charge. Hypobromite, minus 1 charge. Perbromate, minus 1 charge. Now, one good thing about this, they're all the same charges, even though it indicates different oxygen states. Not all atoms are on this, have all available. Nitrate and nitrite are the only ones found. Sulfate and sulfite are the only ones found. And then you may have something like carbonate. Okay, that's a minus 2. There is no carbonite. But this is the one that is most found most often in nature. And so that's the carbonate. Again, you can know this nomenclature, how are they related, and why their names are given, or you can individually memorize each and every anion. There is something about polyatomic ions that have hydrogen. Now, again, you can learn them individually, but what we're going to do is, if you have a carbonate ion and there's a hydrogen in there, a hydrogen acts as a cation, and so what you do is you get a positive 1 for the hydrogen bound to CO3, that's minus 2, and when the plus 1 gets together with this minus 2, the total becomes a minus 1, and I'm going to call this hydrogen carbonate. I say there's a hydrogen and a carbonate. An old nomenclature is bicarbonate. You might know this, like sodium bicarbonate. This is what it is. This is the ion that is in that sodium bicarbonate. Again, sulfate is a ion. If I add a hydrogen to it, then you get hydrogen sulfate. You can see the charge became a minus 1, called hydrogen sulfate. That is the nomenclature that we will use now. It's the modern nomenclature, but if you put a bi, it actually will, it's an old way to indicate that there's a hydrogen there, right? And so adding bi is something that you need to know, because bicarbonate is a very um, commonly used ion, but then the hydrogen carbonate, bicarbonate are used interchangeably because this is established. It's an old name, but used often. And so if you look at a compound and it begins, the first element is a metal, or if you see the polyatomic cation, and the polyatomic cation that we know is this, ammonium, and a nonmetal, you're going to be naming an ionic compound. And so you go through, you have to name the cation first, followed by the anion. The cation, you look and you say, is it a transition metal or one that actually can have multiple charges? If you say yes, then you use its name and a Roman numeral to tell me how much charge it has. Is it a +1? Is it +2? Is it a +3? Tell me what the charge is. The exceptions are zinc and silver. You don't use that. If it is not a transition metal, you just use the metal's name. Then you name the second part, the anion. If it is an element, the element's name gets converted into "ide" at the end. Chloride comes from chlorine, oxide comes from oxygen. Or if it's a polyatomic ion, use whatever the group name is for that, and you need to memorize that. Let's do a couple of examples. Sodium and oxygen, when it reacts, okay? Give the name of the formula. All right, if I give the formula here, sodium reacts, my group scratch work will be sodium +1, oxygen -2, because that's what happens when it gains 2 electrons to form a noble gas configuration. A +1 and +2 do not come together and balance each other out, so I have to use the crisscross. 2, 1, I get sodium, 2 of those, 1 oxygen. And so there is my compound. Now when I name this, it is a metal at the beginning. So it's a metal at the beginning, and I ask, is it in the transition metals? No, it isn't. So I can just write sodium. Okay. And then the second element is oxygen, but remember what we do is anything that has just one atom, kind of atom, oxygen, becomes oxide. I add an I to the end of it. Zinc and chlorine. Zinc, Zn, it's a +2. Chlorine reacts to become a -1. 1 and 1 do not come together, so I have to use the cross method. Zinc, Cl2. And so zinc is a transition metal, but because it's one of the exceptions, I do not use the parentheses. So zinc, I've named the first. It is a transition metal, but it's one of the exceptions. Chlorine becomes chloride. Okay. 2 things are going to react together, calcium and this group called nitrate. So calcium becomes a +2. Nitrate is a group that has a -1 charge. It was given to you. These 2 do not go together 1 to 1, so I'll use the cross method. Calcium, and I have to use the parentheses because I want 2 nitrates. And so calcium is not a transition metal. So calcium and its group, it's a polyatomic group, becomes a nitrate because that's the most common form, and I've memorized that. The next is copper, and I tell you it's copper 2+ by giving you information, reacting with nitrogen. Copper 2+ is what's given. Nitrogen, when it reacts, it gains 3 electrons, become -3. Those 2 do not balance 1 to 1, so I have to use the cross method. That means I have copper, I have 3 of them. The nitrogens that are 3-, I have to have 2 of them. The name for this is, it is a transition metal. So I have to do copper, but I have to tell what charge it is. It's not one of the 2 exceptions that I can just list, so I'm going to say it's copper 2 because here it had 2. Or I can see that if I use the reverse cross method, there was a 2 up there. So, and then the second is nitrogen becomes nitride. And so I have named my compounds. Okay. Some examples. Magnesium perchlorate. Magnesium becomes a +2. The perchlorate, if you look on the chart, it's a Cl04 minus 1. And so if I try to put 1 and 1 together, it doesn't. I would have to use the cross method. I would have to have 2 of those for every 1 magnesium in my compound. This, I have 2 things. It is the ammonium ion and the sulfate ion. So my name would be, name the cation, ammonium, name the anion, sulfite. Calcium nitrate, calcium 2 plus, nitrate NO3 minus 1. I could predict the charge of this off the periodic table. I have to memorize this. 2 things coming together, they do not have the same charge. I have to use the cross method, and I will get calcium, and I need 2 nitrates to balance that out. The next, it tells me it's iron, and it gives me some information. It is the iron, the version that is a 3 plus. I have a sulfide, sulfur. I can look on the periodic table, and that becomes a -2. And so the iron, because it isn't balanced, I use the cross method. Iron, I would need 2 of them. And for the sulfur, or in this case the sulfide ion, I need 3 of those. All right, the next, a little bit more complicated. The metal here is nickel. Now, if you take a look at nickel, nickel is in the transition metals. So that means I have to tell you what charge it is. But I haven't actually told you what charge it is, but I've given that information to you. Right here, there is a 3. 3 would go up on that side. Understood here is a 1, so this becomes a -1. That would become a +3. So in my determination by what I gave you nickel with a +3 charge version, and then the chlorine becomes chloride when it is an ion. The last, stannic oxide, now I gave you a little bit more information. Stannic is the name for tin with a +4. Oxide is a 2 minus. Going back, 2 and a 4 doesn't balance, so I would do Tn using the cross method, 2O4, and then I use this very rare last step. Can this be reduced? In this case, it can be reduced, and so the answer would be TnO2. The last step in making ionic compounds is making sure that you can reduce this fully. And so we have nickel 3 chloride and stannic oxide. Naming acids is easy if you know what the anion is. It's based upon the anion name. So if your anion ends in "ide," then you change the name to hydro in front, ic in the end. If your anion is 8, then I put ic acid at the end, and if it is ite, I put us acid at the end. So it really depends upon what you have. So iodide becomes an ide, puts a hydro in front and an ic acid at the end. So hydro in the front, the iodic acid, because it is iodide. Nitrate, an 8 becomes an ic acid, nitric acid. A perchlorate is an 8 at the end, so it becomes an ic acid, perchloric acid. A sulfite becomes us acid, sulfurous acid. And so, this first one, the anion is cyanide. Okay, it is an ide, so that means I have to put hydro and ic, hydro at the front, ic acid at the end, and that becomes hydrocyanic acid. The next ion is the bromite ion. The ite is the key, and when you have an ite, we change it to an us acid, bromous acid. The next is sulfite. Ite at the end becomes like this, us acid, sulfurous acid. This one, nitrate, ate at the end becomes ic acid, nitric acid.